Hello everybody. Here we are, another snow day, so I thought I would go ahead and finish this lesson with you. You can take notes in your notebook, and then if not, you can always take notes now and then later on transpose those into your notebook or attach them later. Um, so we left here yesterday talking about series circuits. We looked at this example. I know we found the total resistance on the board together. Looked at the current I total because it's equal to all the current in the circuit, I1, I2, and I3. We looked at the voltage across the three components, R1, R2, and R3. We also know the total voltage is 12 volts, so that's our battery or power supply. And the only piece we really had left to do was to verify Kirchhoff's law. That was to add the voltage drop at R1, R2, and the voltage at R3, and those should equal to close to 12 volts. So look at the numbers here for a second. Total resistance, we got the same answer, 1.89 kiloohms. Current passing through each one, well, it's the same current through all, so 12 volts divided by either 1.89 kiloohms or 1,890 ohms, and you get 0.0063 amps, which then could be also written as 6.3 milliamps, like I showed you yesterday. And then IT equals I1 equals I2 and equals I3. Voltage across each one, she got both these numbers, 1.397. I think we're pretty close to that yesterday. The voltage across the resistor 2.984 volts, and then of course the last resistor R3, that voltage drop was going to be 7.619 volts. And then the last step we did not get to do because of time was to verify Kirchhoff's voltage law. And so we add up our three voltage drops at R1, R2, and R3. So 1.397 plus 2.984 plus 7.619 volts, and we have 12 volts. And if, like I said yesterday, if as long as it's the ballpark, it's close, 11.98 or 12.01. As long as it's close, you should be okay. Parallel circuits now, let's look at those. It's a little bit different. Remember, it contains more than one path for current to flow. If a component is removed, then it's possible for the current to take another path to reach the other component. So right now we see two light bulbs in parallel. The electrons could flow through, and if we think about our conventional current going from positive to negative, they could flow through the first light bulb this way, or they could also flow through the second light bulb in this way. If we run a second bulb, notice the first bulb stays lit. Why? Because there's still a path for the electrons to flow. Here are the characteristics of a parallel circuit. So you want to go and write these down. The first bullet's pretty self-explanatory. This total voltage equals V1 equals V2 and equals V3. So what it's saying is if we have 15 volts here at the battery, then no matter where you go in that circuit, they're all going to have 15 volts. So you can go through the first branch of R1, it's 15 volts. Go through R2, it's 15 volts. Go through R3, it's 15 volts. And even you test it down here, when they combine back again, it's still going to be 15 volts. So that's kind of nice about parallel. It's the same voltage throughout the entire circuit. I'm going to look at total current for a second. I'm going to jump down here at the bottom bullet because it's a little simpler too. I total, we just add up the currents in each branch, and that should equal total current. And once again, that is Kirchhoff's current law this time. So what it's saying here, you can measure the total current either the beginning or the end of the circuit. Okay, so right before or right after the battery. But then the current going through each branch, which you could measure here before the resistor or here after the resistor in that branch. Once again, here before R2 or after R2, and then here before R3 or after R3. You would take, say if you measured before each resistor, so the current at this point in that branch plus the current at that point plus the current at that point should equal the total current, which is going to be, like I said, after or before the battery. So that is total current. All three branches or more, could be 4, 5, or 6 branches, add up to total current. Then the last piece here is total resistance. That one's a little tricky. So what you have to do to find the total resistance is that take the reciprocal of the first resistor. So an example would be 470. That's why you see 1 over R1. So 1 over 470 plus 1 over 2.2 K ohms plus 1 over 3.3 K ohms. So it's the reciprocal plus the reciprocal plus the reciprocal. Once you have that answer R total, you have to take the reciprocal of that answer. Yeah, I know. So, and the reason we do this is because every time you're adding a branch to a parallel circuit, you're actually giving electrons more options to flow through. So every time you add a branch, the total resistance for that circuit, the parallel circuit, actually decreases. So a good note to make here is that your total resistance of a parallel circuit can never be larger than your smallest resistor. Because every time you're adding a pathway, you're actually decreasing their overall resistance. So when we do our answer, we should not get an answer above 470 ohms. If we do, then we made a mistake for our total resistance once we find the inverse of our total. Okay, so I don't have a way to have a camera to show you all this, so we have to do it on the PowerPoint. So they want us to find total resistance in the example, the voltage across each component, which we know it's 15 volts, the entire system, so that part's done. The current flowing through each component, so we'll need to find I total and find I1, I2, and I3, and then we'll verify all that using Kirchhoff's current law. So total resistance, like I said earlier, we have to add 1 over 470 plus 1 over 2200 plus 1 over 3300. And once you get that small number, notice that that's a very, very tiny number. When you see this, you're not done yet, but we still have to take the reciprocal of that number to find the total resistance. And that comes out to 346.59. That number right there is less than 470, so it does check out so far. That is being the total resistance for that circuit. The voltage across each component, well, that's easy. It's all 15 volts, so we're done there. Battery's 15 volts, everything is 15 volts. Current through each component, now we're going to look at that. So we know I is V over R, so we're going to take 15 volts, but it's the same throughout, over each resistor's value, so 15 over 470 for R1 to find I1. We get 31.92 milliamps. Do the same thing for R2, so 15 over 2200, we get 6.82 milliamps. And then for I3, so the current in branch 3 right here, all right, try to find that current, we're going to do 15 volts divided by 3300, or 3.3 kilo ohms, and we get 4.55 milliamps. The thing we haven't found yet is the total current. So to find that, we're going to do 15 volts divided by our total resistance, 346.59 ohms, and we get 43.28 milliamps. So I1 plus I2 plus I3 should equal our total current right here that we solved for, and that would be Kirchhoff's current law. So let's check that, add them all together, and guess what? They come out to the exact number. Once again, as long as you're close, that's good, because we chalk that up to rounding error. And then they actually have combination circuits. So you see a series in parallel. Bulbs 2 and 3 are parallel to each other, but bulb 1 is in series to bulb 2. And then also you can see it is in bulb 3. So it's called a combination circuit. So what would happen if we remove light 1? So if we remove light 1, it pretty much kills the entire circuit because it break it right here. Electrons can't jump that gap. And so of course 2 and 3 would go dead. If you remove bulb 2 though, well, bulb 1 would still have electrons flowing through it, and then bulb 3 could stay lit also. It would only affect bulb 2 if you removed it. And if you remove bulb 3, well, once again, since that's in parallel, then that would not affect bulb 1 or bulb 2, so those two would stay on. So that is an upside to having a combination circuit. Electrical power is directly related to the amount of current and voltage within the system. It is measured in watts. You can go ahead and write down that equation. Power is current times voltage, and the units are watts. You want to write that in your notebook. And that is it on this. Real quickly, I wanted to show you something else since I have a little bit of time on this video. I get 15 minutes to talk to you. I wanted to show you about the simulator that I talked about before you left yesterday. So this is for 124. And at 124, I gave you a link. Oh, I'm sorry, 123. 124 is the simple worksheet, just front and back. Please make sure you show your work on that, and then box your final answer in with correct units, and please use proper prefixes also. 123, sorry, that is the bigger packet. It's all mostly simulation. The first few problems, I'll show that real quickly. And while that's opening, I will go ahead and click on the simulator. And the simulator, make sure you have Java updated, and it should work for you, hopefully. And now I'm trying to do too much at once on my poor machine. Okay. So simulator right there looks like that. It is the Circuit Construction Kit DC. And I'm going to go ahead and click download. And this is a newer simulator than what we've used in the past for this class before. So there's a couple of new buttons for it, for me. Let me see if more document ever opened. Yep, there's the directions. So you can also get to the same simulator through that link right there. But I thought it'd be easier just to link it for you on PowerSchool Learning. And then There's an example of what the pictures look like. There's a schematic symbol you'd see in actual schematic. There's the pictures you would see in the simulator that we're going to look at in a second. There's the meters, there's the ammeter, there's the voltmeter. And then these first three problems, they actually want you just to do by hand. You don't have to build it in the simulator. So just draw a simple schematic, kind of like this you see here. Draw one here for number 1. Show your math, box in your final answer with correct units. Same thing, number 2, draw it, solve it. Number 3, draw it, solve it. Then, when you get into this part here about construct circuits on page 3, then you have to use that simulator. And I don't think this is the updated link. I didn't catch that before. But like I said, you can use the link on PowerSchool Learning. And just go through the problems and just make sure you read carefully, because if you notice on number 3, it says construct this, so you construct it, and then test the voltage across the bulb. Well, notice the switch is open. So with the switch open, if I tested the voltage across the bulb, I'll show you how to do in a second, there should be 0 volts going across it, right? Not until step 4, where it says close the switch, then we'd see voltage going through it, and then we'd see voltage drop across the bulb. You can measure that, and then you would write that or record that bulb voltage and the power supply voltage right there. So be very careful about when it says to actually close the switch on all of these steps. Okay? So then they want you to go through and add a ammeter in there, and I can show you how that looks real quickly. I'm going to go and go to the lab since I already know the program. Give it a second. And there you go. So I'm going to draw a circuit. It's pretty simple. Just bring stuff out. Things connect. I'm going to throw a switch down here. So it's a little bit different than what we've used in the past, but still nothing that can't be figured out. Here's my bulb. Notice a positive and negative end. They don't matter how you connect it, at least not for our purposes today. We're just trying to do basic, simple circuit creation. And I typically I have you use this to practice, and then later on we actually build circuits in the classroom. I'd rather have you burn stuff up in here than burn stuff up in real life. So this is a good place to practice. So notice, I'm going to bring my voltmeter out, take one contact on that part of the bulb, the other contact or a probe over here on that part, and notice 0 volts, like I was just saying for step 3. I close it, and voila, electrons flowing, and we show 9 volts at the bulb. I can move these and also see 9 volts at the battery also. Okay, and if I open the switch, well, remember, there's still voltage at the battery, so the battery still shows 9 volts, even with the switch open. Then I can go ahead and get rid of that guy. Bring up my ammeter. I'm using one on the right. That's the one they show in the pictures. I can actually get rid of that wire, click on it, select it, and delete it. And then I'm going to use my ammeter. Remember, we have to break the circuit, when the procedure we went over yesterday. And I drop that ammeter in. Looks like it connected. Yep, looks like it connected, and drag it around. And I'm ready to go to read my current for the series circuit. It is series. Remember, there's only one current. Notice it's showing 0 right now. I haven't closed the switch yet. So I close the switch, and then we have 0.9 amps as our current in this circuit. Something cool that I saw today, you actually can change the current flow. They'd have electron flow, or they have conventional current like we believe in class. So you can use it either way that you want to. That's not the important thing right now. The important thing is knowing how to use a voltmeter and the ammeter properly, how they build a series circuit and a parallel circuit also. I believe that's all I need to show you on this. If you have any other questions, let me know through the Remind app or email me. I'm going to look through this direction real quick again, make sure I'm not missing anything. Be careful. They do change the resistances for each light bulb. And that one right there on number 7. So to do that in the simulator, you would right-click on it, I believe. No. Sorry. Oh, I left-clicked. Sorry. This is a different simulator. And then it allows me to change, so I could change that to 75 ohms right there if I wanted to, which right now is not letting me. I don't want my machine's being difficult today, or I can click, drag, whatever. So yeah, you can do that. Set the actual current or resistance to what they tell you, 75 ohms. Answer those questions. Once again, read number 8. It tells you when to close the switch, so be careful there. They want you to build a parallel circuit. Once again, there's your ammeter. There's your ammeters there also for each branch. There's IT, I1, and I2. So you need 3 ammeters there. And they want you to do a combo circuit. If you have any questions, just let me know, and I will do the best I can to help you do technology. Bye, guys.